In support of high-profile events such as presidential inaugurations, Super Bowls, and G7 summits, the U.S. government deploys many capabilities to respond quickly in case there is a credible threat of nuclear terrorism. One of those capabilities are Nuclear Emergency Support Teams, or NEST, which are sent out to detect, locate, characterize, and if necessary, defeat any potential nuclear threat devices. As part of their response, operators will use mobile radiation detectors to locate and hopefully identify any sources of radioactivity. The challenge is that in addition to nuclear materials of concern, such as enriched uranium or plutonium, there are other possible sources of radioactivity, such as technetium-99, a radioactive material used for medical diagnosis purposes, as well as a background of radioactivity that exists in building materials and natural radiation. Additionally, if a nuclear device is located in a building, materials in the building can shield the radioactive signature, effectively helping to hide the device. Against this challenging backdrop, researchers at the U.S. National Laboratories have created a synthetic dataset that has placed various radioactive sources in the challenging urban environment I previously described to allow for the development of machine learning techniques that could be adopted by first responders to aid in their important mission and hopefully enable the defeat of a terrorist nuclear device.
Hi, everyone. My name is Joe, and I'm part of the Urban Rad Hunter team. And our team is composed of our faculty, Robert Burchin, Tom, James, Gregory, and also the researchers, Peter, myself, Jose, and Lindsay. So when we see a symbol like this, we automatically think about a nuclear bomb or a radioactive meltdown at a plant. But the sources of urban radiation can be more diverse than that. And just to give you an example, I just want to talk about this case called the Goiânia accident in 1987 in Brazil. And essentially what happened is two scrappers were going to an abandoned building. They came across this old medical equipment, but little did they know that there was cesium-137 in there, which is a highly radioactive material. But they took it apart because they thought they might find something valuable. And upon finding the cesium, they distributed it to lots of people in the community. And at the end of the day, there were 4 acute deaths, more than 200 people with high levels of radiation found in their body, 6,000 tons of radioactive waste generated, and of course, a community that was traumatized after this event. So all across the world, there are radiological events that are happening all the time. And this is just a map showing just events happening across the globe with darker colors showing more events. And in this 6-year period of time, there are over 1,200 reported events. And we have tools to detect radiation. For example, we have scintillators, which can detect gamma rays emitted from radioactive sources. And in pristine environments like this, these are pretty effective using traditional signal processing methods. But in an urban environment where sources might be shielded by buildings, or the buildings themselves are emitting gamma rays, which can confuse a detector, it's not so easy. And also the sources themselves might be moving around in this environment as well. So essentially this boils down to detecting a faint signal in a complex and noisy environment. And we know that machine learning is very good at detecting and identifying the signal from the noise. So the question we want to answer is, can we apply machine learning to outperform traditional signal processing methods for our application? And the goal is to develop a machine learning algorithm that can be deployed on existing detectors. And we did this by using simulated data, as the video mentioned, that was provided to us by the Department of Energy, and it simulates a detector moving through an urban environment. And here on the right is showing gamma rays dispersing through the urban environment from a radioactive source. So you can imagine as the detector is going through, it's logging all the energies. And for a given time slice delta t, we can form histograms based on those energies. And if you form histograms for every delta t, we can stack all these histograms and form an image. And we know that we can do image classification very well. So that's the approach that we took in our challenge. So given these images from lots of different runs, we want to separate the background from the source runs. And that can be done using a binary classifier. And furthermore, we want to know what kind of source is in these source runs, right? And then we can use a multi-class classifier to do that. And I'll hand it over to Jose to talk a little bit more about our pipeline and our preliminary results.
Thank you, Joe. So here's our framework. It's the RedBot. Essentially, is a tool that can detect and identify the radiation, and that can be also built into devices and run into urban environment as well. To build this, it starts with the data processing, where we take the raw data and transform it into a bunch of images and put this to train our models. Then we assemble them to a bunch of modules with different features to get better predictions on that. Right. After we assemble the model, right, we can test this with simulated data or put into the real world. So basically, is the flow of a pipeline. But this we need detection in real time. So we decided to slice the full run image into slices, the small chunks that can become our trained images, right? We separate those slices into source or not source and different kind of radiation sources. But this still classify on these slices. If a detector passing through is a part of the run that classifies a source, the next one might not be classified as the same one, and we need some other kind of approach of that. We need to see if the next, let's say, 6 runs is also source, and then we apply some heuristicals to infer if there is another source and make the decision. Right? So we train our model and we get a validation around 87%. So, but this was training our model with around 100,000 images, and we are scaling up our model up to 5 million images and much more features to train it. But in fact, this after training is real fast to infer whether there's a source or not. It's less than a second to inference if there is or not. And in summary, our approach is like faster than before, because we don't need a full run to predict if there is not a source of radiation. We can detect in the full run during the run. We also have much more data, and augment the data and apply different channels to those images with different features that can be also understood as kind of things to identify the source. And we assemble more than one model as well to get better results on that. So I will leave you with that video. With that, we can imagine a drone with detectors and the building a framework that are measuring the radiation in the urban environment, and can automatically detect if there is another source of undesired radiation, that make alert and make this to decision makers to have a decision. So thank you very much for your attention. It's the RedBot.
Excellent. Thank you so much. Both teams, RedBot and Astrobiology, really sensational stuff and beautifully presented as well. I wanted to introduce our Y panel. I realize there's a bit of a difference in domains here, but of course the theme is signal in the noise. And we have Craig Sloan from the DOE, Ritwik Gupta from UC Berkeley, John Karch from NASA, and Mary Wojtek from NASA. So welcome. Really looking forward to hearing your thoughts. Two sensational bits of research, and yeah, just to sort of see what you thought and what surprised you, and And perhaps actually, Craig, why don't you pick up the baton, and be good to hear your thoughts.
Yeah, thanks very much. No, that was outstanding from both teams. Obviously, I'm a lot more focused on the Urban Rat Hunter, the Radbot one. But you guys absolutely nailed it from my perspective with regards to understanding the challenge, but then understanding the importance of the challenge and the fact that you've got to make these decisions in near real time. And so you can't have these overly complex algorithms that will take minutes to half hour to an hour to run. The people doing that search need to be able to get some sort of determination in real time. And the fact that your algorithm that you developed is providing those results in less than a second is outstanding. And that's what we're looking for. And so, you've really done really nice work here that will have some real world applications and potentially can save lives in the future. So I think you should be very, very proud of what you've done here.
Ritwik, I saw you nodding. I don't know if you want to build on that.
Yeah, first of all, fantastic work to both teams. Clearly a lot of effort put in here. The single most common thread between both of these presentations was how they're using machine learning to wrangle this task of complexity. Urban Rat Hunters trying to find radiation in complex urban environments. The other team that I'm blanking on the name of right now is trying to characterize complexity of molecular data. But we don't see this often in machine learning. We're doing really well at creating new images, at generating new text in simple, sometimes unconstrained environments, but actually understanding fundamentally what makes these data complex and how can we detect them in these really chaotic environments. That's a field that's really underexplored. And these teams have done a fantastic job. Urban Rat Hunter, your work could be equivalently applicable to finding radioactive sources in new planets where we don't understand what processes cause radiation or how different atmospheric layers could make radiation go in different directions. So really good work, really excited for the future of your projects and looking forward to how all of us can help you to get to this better future.
Thanks, Ritwik. So speaking of life on other planets, Mary, do you know what you were thinking when you saw that? Mary, did you want to make some thoughts on how the teams went? Not sure she can hear us. John, do you want to jump in? Yeah.
Yeah. So first of all, I think it was great having these two teams together. I can really see the connection between them. And, starting on the astrobiology front, I think that
I thought this was an amazing challenge. And I just want to highlight a few things that I think the team brought up in their presentation. Okay, so I'm sorry for the delay. I'm not sure what's going on, but